全世界都知道我这个做。后边的。哎，对对对。
Okay, we're going to start the next talk on time, 11 o'clock, so that we could get to lunch on time. That's important. Okay. So our speaker will be Professor let me see. I know from University of Missouri here. I have the first name. I'm sorry. Yeah, Professor Giovanni Vignale. That's my colleague.
Just the second tone of Italian language.
Yeah, that's very hard to pronounce. Yeah. Okay, from University of Missouri in the United States, and that's a beautiful campus. That 6 columns, I know about that. And he's going to tell us the same title here. So, magnetotransport driven by interfacial spin orbit scattering. So let us welcome our speaker.
Okay, thank you very much. So I'm happy to be here for the second time. This is my second visit to Taiwan, and I must say I like the weather much better. At least the temperature much better. And I only hope the sun also shows up at some point. Okay, so what I wanted to tell you about here is some of the things I've been doing in the last year, a couple of years on spintronics, and in particular on what Fert calls orbitronics, so that branch of spintronics in which you use spin-orbit interactions to control the spins. And even more specifically, the work I will present has to do with the effect in which the presence of interfaces between different kinds of materials and the spin-orbit interaction of those interfaces plays a crucial role. So, let me begin by giving you an idea of the kind of systems that are being considered. First of all, one thing I wanted to mention is that it seems to me that spintronics has come a little bit under pressure in recent years. Of course, the great achievement of spintronics was the giant magnetic resistance we had, quick commercialization and fusion. But you see, the computer on which I'm giving my talk here, it has a solid state drive. It's all flash memory. Okay? So I don't know if this is a game that the industry is playing, planning the next move. But taken at face value, it doesn't look good for spintronics. So it seems that spintronics should really come up with new ideas, and perhaps some of those new ideas will have to do with spin-orbit interactions and interfacial effects. Okay? So here is some of the structures that I will be talking about. Now, this, frankly speaking, makes me think a little bit of those Hollywood movies in which you combine all the characters in all the possible situations, and out comes a plot for the next movie. Here is the same. So you take all kinds of different materials and you put them together. So, for example, this first structure that you see is the one that was used in a by now very well-known experiment by Professor Sanchez, which demonstrated the spin charge conversion, also known as spin galvanic effects, or also known as inverse Einstein effect. Here is interface between silver and bismuth. Okay, so in this structure, you see lots of things go on. You start with a ferromagnetic layer in which you pump a spin wave that produces a spin current that travels to the silver, is presumably absorbed at the interface between silver and bismuth, and eventually it generates this inaccumulation at the interface generates an electric voltage. There will be a transverse electric current here at the interface, which is detected as a bottle. Okay, so this is an effect that has been seen. The interpretation is not.
Giovanni, I think we cannot hear. So
oh, okay. Okay, so sorry about that. The interpretation is not completely unambiguous, because part of the signal will be due to the inverse spinol effect, but nevertheless, this is a kind of system that has attracted a lot of attention. Now, another system about which I'm going to talk is this simple, metal insulator interface. The insulator can be a vacuum, and the metal is typically, in my talk, a heavy metal, so something that has a significant, strong spin-orbit interaction. And we will see that interesting interfacial phenomena like spin accumulation so occur. And then this is, for example, a system that has been the subject of very many high-profile papers in recent months, years. So here you have a ferromagnet, permalloy, grown in fact on top of an insulator, in this case a topological insulator, to make it even more interesting. And what happens is when you drive a current when you drive a current through the surface state of the topological insulator, that creates a spin accumulation, which again generates a spin current, which applies a spin torque to the ferromagnet. So it's a way to control the magnetization of the magnet. Okay. So last but not least, I have a lot to say about this. This is probably the most interesting part of my talk. There is this kind of structure in which a heavy metal is put together with a ferromagnetic insulator, like Ig, garnet, and you can observe some really exotic effects, such as a new type of anisotropic magnetoresistance at the interface, as well as a non-local anomalous Hall effect, which I will try to explain in detail. Okay, so it's basically a Hall effect which is controlled not by the magnetization in the metal, but by the magnetization that is far away in a different layer. Okay. All right. So here is the outline of my talk. So there will be basically three topics here. So one is I will show you. I will tell you about the current-induced polarization at the surface of a heavy metal. Then I will tell you about spin torque generation and anisotropic magnetoresistance at the interface between ferromagnetic metal and the insulator. And lastly, this non-local anomalous Hall effect, which I already mentioned. Okay. Most of these things already have some kind of experimental verification, but more work is needed to, disentangle, clarify the various possible alternative interpretations. Okay, so let's begin with this current-induced spin polarization at the surface of a heavy metal. Okay, so it could be gold, but even better, platinum or something with even stronger spin coupling. So I will start with something very simple, something that appeals to a theorist, a very simple model which allows us to prove a theorem about the spin accumulation that occurs at the interface here. Okay, so here we go. So the model, as you see, is basically a gellium surface. Okay, so it's essentially a potential barrier. A generic potential that rises from 0 to some barrier value. Okay. However, this is the heavy metal has, of course, strong spin-orbit interaction in the bulk, but within the bulk, because of the inversion symmetry, there is no spin splitting of the states. The situation changes at the interface, where you have a broken inversion symmetry, and that creates a spin splitting, also known as Rashba effect, Rashba field. Okay, so our model includes not only the scalar potential barrier, but also a piece that couples to the spin of the electron through the electric field, derivative of the potential with respect to z. Okay? Now, the strength of this interfacial spin-orbit coupling, I call it interfacial because you see it's proportional to the derivative of the potential, so it exists only near the interface. It's zero otherwise. Okay, so the coupling constant, of course, is not very well known. If I were to do, if I were to take the Vignale model literally, I should say that this is essentially, you know, this related to Compton wavelength. Okay, it's h bar over 4mc squared is the ideal Vignale model value. Actually, we know that in a real material, this is not so, and it can be several orders of magnitude larger. But bear with me for a moment, and you will see that we are going to play an interesting game with this. Okay? So for the time being, this is a gamma. And notice that also the sign of this gamma can be either positive or negative, again, depending on the details of the band structure and so on. Okay, so this is a textbook problem in which you can solve exactly for the scattering states, right? So there are plane waves with wave vector q parallel to the interface, and of course there is the wave function with momentum k, depending on the coordinate z perpendicular to the interface. Okay? And so you have reflected waves and transmitted wave, and we are actually in the regime in which there are no transmitted waves. There is only an evanescent wave past the barrier. Okay? So now, what we want to show is that if we put a current in the metal, in the bulk of the metal, okay, so there is a current flowing along the x direction, okay? And that current will induce a spin density, which is bound, essentially bound to the surface, okay? And the integrated value of that spin density is universal. There is a theorem here, okay? So it just goes like this. So you calculate the spin density just from, as a function of z, just from its definition, right, in terms of the Green's function, okay? And then you calculate this Green's function perturbatively to first order in the spin-orbit interaction. Okay, so the barrier is treated exactly, but the spin-orbit interaction is treated up to first order, and you arrive with something that you see contains just one derivative of the barrier potential. And now you observe something very interesting, that this v prime, the derivative of the potential, is the force, right? And the expectation value of the force in one of these scattering states is really the momentum that is the force exerted by the surface of the electron, right? So it's basically the momentum that is absorbed by the electron as it interacts with the surface. So you have an electron coming in with momentum k and reflected with momentum minus k, so a momentum transfer of 2k at the velocity k over m, so the flux of momentum is 2k squared over m, and you can show that the expectation value of the force in this state is exactly 2k squared over m, on really very general considerations. Okay? And the result is using this thing, all the dependence on the potential disappears. Okay, so that's the beauty, the generality of the result. And the spin, the total integrated spin, turns out to be just our famous constant gamma times z, the normal to the surface, cross j. So it is in the plane, so the spin lies in the plane of the surface, it's perpendicular to the current, okay? So, okay, so z cross j. But the important thing for our purposes is that it is proportional to that gamma and does not have any specific dependence on the forward potential. Now, on the other hand, now all this looks nice, but it's you know, very academic, right? Because, as I said, in a real material, we don't know exactly what is gamma, and so what should we do from this point? Well, what we can do is now we go to our friend Eugene Krasowski in San Sebastian, and we ask him to do for us an ab initio calculation of you know, basically the surface of gold. Now, this could be done also for a stronger, you know, the coupled material. And here what comes out, okay, so you see that the spin density plotted as a function of the coordinate z, right, the coordinate perpendicular to the interface with the vacuum is this, okay? And here you see, you know, there's a lot of information here, okay? So there are certain oscillations which are, you know, associated with the crystal structure of the gold, and then there is a big spike here, which is the effect of the truncation, the effect of the surface, Okay? Now, from this mess, you have to subtract the part of the spin. So I forgot to say a very important thing, that this whole calculation has been done in the presence of a current. And the presence of a current means that we have displaced the Fermi surface in the parallel interface direction by a certain amount Q, which is proportional to the current. Okay, so that's how the current is put in the calculation. And that's what causes the appearance of this spin density. Okay? So there is, as you see, a kind of bulk contribution which is periodic and integrates to zero. Okay? If you look very carefully, you realize that there is also a dipole spin contribution, which is more subtle and reflects the bulk spinor effect. And they would have a lot to say about that, but they will not for the time being. And then, see, when you subtract from the full results the periodic components, what you are left is this. What you are left with is this red curve, which clearly shows the spin accumulation, and you can, from this, extract, by integrating this, you can extract the effective value of gamma, the effective value of the spin orbit constant for the material, for the gold. Okay? So, so the logic is this, okay, that in some sense, this complicated material, this piece of gold, is equivalent to a Gellium model, okay, as far as this property is concerned, but with a value, an effective value of gamma, which we have calculated from first principle. And hopefully this gamma can now be used also to calculate other transport properties, not just this spin accumulation. For example, to calculate the spinor effect, just to make an example. Okay, now there are two more points that I want to make. So the first one is that the value we extract for the gamma here is actually extremely close to what has been estimated for gold precisely from measurements of the spinor effect. Okay, this is the value. So there are some conversions to be made, but I remind you that in our previous slide, the calculated value was about 0.2, and this is about 0.1. Now it's up to you whether you consider this good or bad. To me, it's not bad at all. Also, I want to point out that the contribution of the surface state, which exists, of course, in real gold, okay, but doesn't exist in our Gellium model. So that is a thing to worry about, right? Because there is a qualitative feature that is not captured in our model. But fortunately, it seems to be a very, very small contribution. So if you look at the scale, it's really much smaller than the bulk value, let's say. So most of this effect comes from the scattering of states coming from the bulk and returning from the bulk, okay, without really any significant contribution from the surface state. And this, you will see a theme in my talk, that many of the things that are at least fashionably ascribed to surface states, they actually can be very well explained by a much larger contribution from scattering of bulk states. Okay, so this was more or less the story for this surface accumulation. And
one simple question.
Yeah.
If the surface is not abrupt, but let's say less abrupt, then
Yeah.
does it change this effect gamma?
Right. So in the model, of course, it's completely independent. So if you make it less abrupt or more abrupt, the result is still the same. But of course, in the ab initio calculation, the details of the surface are going to matter. Okay. And then, so you will find, in other words, depending on the details of the material and other things, you will find a different value of that effective gamma. But the theorem says that in the Gellium model, the accumulation is independent of the shape of the value. Okay. All right. So let's move on now. Oh, okay. So I forgot to mention another interesting thing. There has been measurements pretty recently in this last year's scientific report of experimental measurements of this spin accumulation in a number of heavy metals with a current flowing. Okay, so this is done with a technique that is called spin polarized positron beam, in which basically they look at the positrons in the beam forming bound states with spin polarized electrons on the surface, and from that they are, by some black magic, frankly, able to extract parameters such as the spin polarization of the surface. Now, if you look at this table, you will see that for our system gold, the spin polarization, they call it null, but it's actually not null, but it's, it corresponds to a very, very small value which is below their threshold of observation, and which actually is consistent with the numerical values that we calculated in the Krasovsky calculation. So it's, we found really small polarizations which are consistent with their inability to observe them. Now, when you go to higher, strongly spin-orbit coupling materials, like, I don't know if you can read this, but I myself cannot, it's platinum, okay, or even better, this alpha tantalum, you see enormous polarizations, okay, 11%, 12%. This is spin in the plane of the surface, okay. Now, whether this can be really explained completely by, an ab initio calculation remains to be seen. Okay, so I don't know. Definitely, the calculations that were done so far didn't give such large value. They gave much smaller polarizations. Okay, so now let me come quickly to the second point. Spin torque generation and anisotropic magnetoresistance at a ferromagnetic metal insulator surface. Okay? This is the Vignale's research group. Okay, the man behind the work. All right. So, he's done not only this work that I'm going to describe now, but also the next one, the one on the non-local anomalous Hall effect. Okay, so the model we have in mind now here is very similar to the previous one, but there are a few differences. First of all, we just take a step function for our barrier. Okay, so we don't need anymore, a generic potential. Secondly, we now consider a ferromagnetic metal. That's the essential difference. Okay? Before there was no magnetism in the metal. Now the metal is ferromagnetic, and the magnetization points you see are perpendicular to the interface. Okay, so this clearly, okay, so in the Hamiltonian, this is reflected by the presence of an exchange term. Okay, it splits the energy of the spins in the bulk. Otherwise, the structure of the barrier, but we have a step function, and you see we have the interfacial spin-orbit interaction, which is now a delta function, because it's the derivative of the step. The Fermi wave vector, the Fermi momenta of the electrons at a given energy are, of course, spin-dependent now, and that's an important difference. Okay, so we can solve this problem. So the theoretical framework, in this case, consists of the following steps. First of all, we write down the Boltzmann equation for describing the current carrying state in this material. And then we need, and this is a very important thing, okay, which I think it has a future in the field. Okay, so we have to really learn how to describe these situations with effective boundary conditions, because we really don't want to go too microscopic most of the time. We would like to work. In fact, even the Boltzmann equation is too microscopic. Okay? Ideally, we would like to work with drift diffusion equations with the right boundary conditions. Okay? And here is the particular boundary condition that we use for this problem. It relates the distribution of the incoming electrons, the F minus, to the distribution of the outgoing electrons, by which I mean electrons reflected from the surface. Okay? And basically there are two components here. There is a specular reflection component, and there is a diffuse reflected component. And the idea is that the specular reflection component is rotated coherently in spin space by the interfacial spin-orbit field. Okay, so this is what these metrics does. So it changes the distribution, the spinor distribution, right, in spin space. Whereas the diffuse scattering thing is not so rotated, because the assumption, at least in the model, is that the diffuse process erases all the precise phase relationships of the wave functions and so on and so forth. Okay, and of of course, the spin rotation matrix R, which appears in the boundary condition, is perfectly calculable and expressible in terms of the parameters involved, which is done, such as value height, and etc., the momentum of the incoming electron, and so on and so forth. Okay, so these are, by the way, called Fuchs-Sontheimer boundary conditions, and they were used long ago to calculate, for example, the contributions of the surface to the resistance of a metal field. Okay, so they have a long history. All right, so now, okay, so let's see what happens here. In a first example, I want to show you this phenomenon of surface-induced spin torque. Okay, so basically the idea is that you have a current coming in this direction, right? In this figure along the x-axis, just an electric current. Okay, but remember you are in a ferromagnet. Okay, and the ferromagnet is polarized in the z direction, so the charge current automatically carries also a spin current because there is a spin polarization. Okay, so now these electrons are reflected from the surface, and at the surface there is this interfacial spin orbit field which points in the y direction. It's the Rashba field that twists, that causes a precession of the spin, and as a result you see the spin that emerges from the reflection as it's spin tilted that way. Okay? And then of course it requires also a component in the perpendicular, a component of momentum going away from the surface. So the result is that the original spin current propagating in the x direction with spin z has been transformed, at least partly, into a spin current propagating in the z direction with spin x. This is called the spin current swapping in the terminology of Diakonov and Lifshitz and Diakonov. Okay? So if you ever worried what spin current swapping is good for, well, that's an example. Okay? Why this is interesting? Because clearly, you can now transfer momentum to the magnetization of the magnet. So you can affect the dynamics of the magnetization of the magnet. That's the idea. So I have here a little animation that shows how the spin hits the surface. This specular reflection interacts, you see, with the Rashba field, which changes its direction. Okay, and then it takes off. Now I guess the program is calculating according to our formulas. So, and then you see, as it takes off, it starts precessing along the direction, around the direction of magnetization, until eventually it aligns. But during this process, it has really exerted a torque on the magnetization. Okay? So this is very similar to what happens in these Melnick-Ralph experiments at Cornell, except that in their case, the source of the spin torque was an accumulation at the surface of the topological insulator, much more fancy. Here we have only bulk states reflecting from the surface, but they essentially do the same job. And in fact, you can calculate the spin current emerging from this reflection process, and you can calculate the torque, which is just the integral of the divergence of the spin current. And here it is, and we have plotted it here. So just as in these Ralph Cornell experiments, you can see that the spin current has two components. Okay, so one in plane, in the plane that I was showing in the previous figure, and one perpendicular to that plane. They're both present. But now a very interesting observation here, and this is something that should be observable experimentally, is that the sign of this torque depends very strongly on the asymmetry of the conductivity in the magnet. So this parameter P is the difference between the conductivity of spin up minus the conductivity of spin down divided by the average conductivity of the two components. This result that you see arises entirely because there is an asymmetry in conductivity of the two components. Okay, so without that, you basically would not generate the spin torque. And now the interesting thing is that this P can be either positive or negative depending on the choice of material. You see, here is a table dating back to an old paper by Campbell and Firth, which shows that, let's see here. So for example, if you look at iron, the asymmetry between majority and minority spin conductivity is 0.9. If you go to chromium, it is minus 0.38. So there is a change in sign, okay? And this will reflect in a change in the sign of the torque, the generated in the interface. So basically by changing material, right, you should be able to see, if you do experiments similar to the ones performed by the Cornell group, you should see a sign in the torque transferred to the magnetization, okay, which is internally measured through by looking at ferromagnetic resonance shifts and so on. Okay, so this is the story, but let me come to a very interesting effect that we uncovered here. That is the peculiar anisotropic magnetoresistance that occurs at these surfaces. Okay? Now, let me remind you that the ordinary anisotropic magnetoresistance is a bulk effect in which the resistance is found to depend on the angle between the current and the magnetization. Okay? So typically the resistance is high if the current is flowing parallel to the magnetization, and it's a little lower, maybe a few percent lower, if it is traveling perpendicular to the direction of the magnetization. So the key dependence is through the angle between current and magnetization. Okay, so now this effect was the basis for the first generation of magnetic reed heads. Okay? Before the giant magnetoresistance took over, what was used was the anisotropic magnetoresistance effect, which is much smaller. Okay? So it has a history of useful applications. Okay? So now what happens is, the question we can ask is, will the interfacial spin-orbit interaction affect the anisotropic magnetoresistance in the ferromagnetic layer? Okay? And the answer is that yes, we find that in the vicinity of the surface there is a significant correction to this, a qualitative correction, we should say, due to the fact that the spin-orbit interaction transfers momentum from one spin channel to the other, to that spin rotational effect. Okay, and so the total in-plane momentum is still conserved in a specular reflection, but the momentum can be transferred from one spin component to the other, and as a result, you can have a magnetoresistance, as I show you now, which depends not only on the angle between current and magnetization, but also on the angle between the magnetization and the normal to the interface. Okay, so let me be more clear here. Okay, so maybe it would be better to look at this figure first here. Okay, so here is the interface. Okay, so here on top you have the ferromagnet, and below it you have the insulator. Okay, so the current is flowing in this direction, the x direction, and the spin-orbit field is in the y direction. Okay, now let us say that the magnetization can rotate in the YZ plane, okay? Going from, you see, parallel to Y to perpendicular to Y and then back parallel to Y, okay? Notice that in this situation, the angle between the current and the magnetization remains constant, 90 degrees. Okay, you see that the magnetization is in a plane perpendicular to the current. So according to the usual bulk anisotropic magnetoresistance, there should be no effect whatsoever. Okay? But in fact, there is an effect. Okay? And the effect comes because you are changing, when you swing the direction of the magnetization in this plane, you are changing the angle between the magnetization and the Rashba field. Okay, so let's see what happens